There's a fantastic animation made by Josh Lees. I'll put it again so you can appreciate it. He has many more movies and a nice website. He's an engineer who's now doing a lot of fantastic work illustrating mathematics, between art and math, and highly recommend it. We are discussing gluing polygons, and nothing best than a picture to show what happens, when you start with an octagon. Here we're doing every pair of edges. This is different than what I did last time. Mainly I was discussing some pairs of edges in polygons. Here he's gluing them all, but couldn't resist showing this. That was the reaction I was hoping for. You passed the test. Yeah, not the first time I watch it. Every time it's wonderful. Okay, let me just say a couple of things that I forgot to say, and probably I forgot more, but made my about the play. Maybe we can meet at lunch, whoever is interested in helping me. Some people like to read, but some people have an idea of stage direction. I'm a writer, so if anybody has an idea of how to direct or something and wants to help me, that'd be wonderful. Some of them will be on stage, but you will not be forced. So let's sit together at lunch. You can only sit with me if you want to help in the play, and then we'll talk about it. Now I want to do very quick unsolicited advice, because I've been talking to some of you who mentioned things, and I just wanted to open the discussion. There are very simple things that you probably thought and talked about, but if you didn't, many of us have the impostor syndrome, the thing that they are going to discover that I'm not good enough to be where am I, and what happens then. This is a good thing to talk and see that many people here, I talk to some of you and you all have credentials and brain that shows you deserve to be where you are, and still we keep doubting and wasting our mind in thinking about that. So maybe seeing that other people have the same issue will help. The same thing, we lack of confidence, and I say we because I am, included. It took me, I'm 51, and it took me decades I feel a little better right now. I wish you could do it faster than me. So, and for me, what it helps here is it's here. When I have to give a talk and I'm nervous, what I think is it's not about me, it's about the math. I feel like I'm a servant of math, which is something I adore, appreciate. I want to serve to the best of my ability. That's the only thing I can do. So when I start to think about me, am I good enough, blah, 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 I think it's not about me, it's about the math. That's my mantra. Maybe you can find yours. So just work hard. And the other thing, I made a mistake, is sometimes I see people and I try to, oh gosh, these people is so great. You look at Moon's style, her style is wonderful. I cannot be Moon, You can only be yourself. So be your best self. It sounds obvious, but we do try to think, oh, this person is great. Why am I not like that? I know. And then, this is the last I didn't write. And it's a silly technique, but for me it works. If you're worried about something, these worries that you shouldn't be worried, is totally unnecessary. What I do is I set up a time of the day when I worry about that. Say, okay, I'm going to worry about this. I swear, from 7 to 7:30 today. So every time the thought comes, I said, okay, I'll think about it from 7 to 7:30. And maybe you sit and think about that the most productively you can, but you push it to a certain time. You have a time of the day to worry about these things. Okay, now let's do math. Okay, so I'm going to do a quick review of what we discussed last time. Remember that we were talking about surfaces with boundary. This is a torus with one boundary component in red. And then we're going to cut these surfaces with cuts that go between boundary component. In this case, the cuts are drawn in blue and green. And then you will open up. I was going to do an animation, I forgot that. So this is the open up surface after I cut with the scissor like that. The rules of the cutting were, you're not allowed to separate the surface in two pieces when you cut, and of course, cuts do not, you don't over a cut, a cut doesn't go over itself or other cut. So those are the cuts. And then you're going to label, let's see my pointer here. Then you're going to label the edges. Well, here are colored, and the color will be enough to remember, who was glued with whom. But later on, you cannot color everything, so you put letters. And you put, the same letter. You see I have different capitalization of the letter. That will be used later. Right now, I only need to know that green is glued to green and blue is glued to blue. Then I'm going to copy the letters I got, the pattern to glue my, this is an octagon. And this is A, B, capital A, capital B. And this is a cyclic word. It's like a ring of letters. Sometimes I say a word, most of the time I mean a cyclic word, an oriented ring of letters. This word, as I said, contains the surface secrets. It really gives you the information about the topology. Of course, together with the algorithm I just described, we used to find this surface word. Okay, so if I give you this naked, it's nothing that you can do. But if you know that you have to label every other edge of a polygon and glue them with the same letter, then you obtain the surface. So this object is a surface word. So it's a cyclic word. I'm using Moon's word. In a symmetric alphabet, this is an alphabet that contains, letter and letter capital, letters, with opposite capitalization, with the property that every letter occurs exactly once. So I want to reconstruct this thing. So I have to have an alphabet which is finite, has an even number of letters, and the letters are organized in pairs. So this is a surface word. And we said that, well, except this example, for instance, for the torus is very simple. And if you try to find other word, did you try to find other word that given the same surface in the review session?
Yeah.
Yeah, and?
We did.
For instance?
For the case of genus 2.
For this?
For this one? Yeah, we did a octagon, for example, I think. I don't remember.
Anybody remembers this? Yeah.
With more boundary components.
Okay, with more boundary. For this one, I was tricking you. Yeah. Exactly. So really, this is the only word up to, very, a bit obvious permutations. But as Loli said, in other surfaces, you may have more words that give you the same surface, that are essentially different, that you cannot go one to the other with some obvious way of flipping or rotating or something like that. So still, these words are really good. I'm going to keep proving it today. So then, once we fix a surface, and then we fix a surface word. So this is fixed. The way of cutting our surface is fixed. Then we're going to look at curves on that surface. And then we're interested again in curves up to deformation. And again, to each deformation class of curves, we want to assign a word. This will be a different type of word, okay? Because we have surface words and curve words. They are different. They're both made of letters, but they have different rules and different nature. So the surface word, here is the surface word we associate to the class of this purple curve. So it's easier to see it sometimes, when you open the surface. This curve here follows the same combinatorics as the curve on the torus. And the way you obtain the surface curve is you start at any point. We are looking curves that we don't know, they don't have a beginning or end, it's just a loop. So you start at any point. Here, I go to the edge labeled by capital B, and then you come out exactly where you glued. This is the edge labeled by small b. We don't record the small b. We record the capital B where we enter. We go to the edge labeled by A, come here, go to the edge labeled by B, and then you keep going until you come back here where you started. So I record this, this is this cyclic word is very well adapted to these classes of curves that I'm thinking that I have no beginning point. Some of you might have studied the fundamental group of a surface, and here you're looking at loops that start, they have a preferred point where they start and end. And then if you know a little more, you know that those, you can associate words to those too in the case of surfaces. Well, these are like those, but instead of, there's no beginning, so the words go in a circle like the loops, no preferred letter to start, no preferred point to start. So these words contain, what are the rules? So they can contain any number of letters. Every letter can appear as many times as the letter wants or doesn't want, maybe 0, maybe 175. And there's one more rule. Anybody can remind me?
Different capitalization here next to each other. So A and A capital.
Exactly. You cannot put different capitalization next to each other. So A inverse or B and B inverse, the capital, I remind you, was inverse for me, cannot be next to each other because this will be, if I want to draw this, so if I do say I enter through B and I go here and then I go B bar, so I did B bar, I'm going to have this little loop go from here to here, which is something I can push, I can deform out. So it will be a very inefficient way. Therefore, the rule is any word is allowed, but I cannot have two letters with a different capitalization next to each other. And ta-da, here is a wonderful theorem that says that if we have a surface with boundary, we have a bijection between the curved words and the deformation classes of curves on that surface. So meaning that every deformation class has a label, and the label is this curved word. Any question? Nope. Okay. So, by the way, I put it now I did put the slides. Yesterday I said I put the slides on my website and I lied. So you don't have any reason to trust me today. But I put it in PDF and I put it in this word form that you can see all this suspense that I add, put in figure by figure. So it's there. I mean, I see some of you copying to say that. So now we're going to study the crossing points, the intersection points, self-intersection points of curves on surfaces. Remember that I said, well, we have a deformation class of curves. You fix the surface. Now, let's fix the surface from now on. If I forget to say, you remember it in your head. And now you want to say, well, the self-intersection number of the class of curve is the smallest number of points a curve on that class intersects itself. And remember that we count, intersection for us is the section of pairs of arcs. So this counts as 3 intersections because basically this is like this up to deformation. So we want to study the intersection number, and we're going to do even more than that. We're going to, each intersection point, we're going to label it. So we're going to be distinguished in some way. We're going to label it using the curved word. So let's look at our first intersection point that we discussed last time, this one here that I highlighted in blue. And I also highlighted the 2 pieces of curve that cross and make that intersection point happen. So you see, if you ask, well, what this piece of curve is on my curve? Well, I'm going from this edge to this. This is the label by small b, and this is the label with capital B. Now, if you start at the small b, means that you have to enter through the capital B. So you enter through the capital B, and then go to the B again. So this particular segment is in this curve because my word has a subword which is of the form capital B, 2 capital B together. Basically going, this is not, this happens in every surface, similar things. It's just I'm going from here to here, and these are 2 letters, and the corresponding letters will imply a segment like this. Same thing here. This is because I have an AA. So every time I have a word that contains, a curved word that contains an AA and a BB on a torus with boundary, I will have a crossing. Of course, somebody made a very good observation yesterday. This depends on the surface word. Because here BB means this and AA means this. But if BB means this and AA is this, if this is BB and this is AA, here there's no crossing. So, but the surface word here tells me this is a crossing. So what I'm going to say a little faster now is, but let me just say it first, each point can be labeled by a pair of subwords. Here, this is my word. I wrote it linearly, not because it has a preferred letter, but because it's too painful to write circle words. So here I highlighted the two subwords that imply this crossing. Yes?
Sorry, could you explain again why it implies a crossing? I don't understand why you can have like two parallel lines or something.
Oh, you can. But if you have two parallel lines, like this, so suppose I have something like this. Yeah. What word corresponds to my arm? What subword? Why do I need to have my arm here in my circle word? I have here a capital A. So this means I enter with a small a.
You had to go somewhere else.
Right.
Okay. So the upper also be yellow, right?
Yes.
That one's like B, A, and A.
Yeah, wait. You're too fast. I'm going there. So this is one type of crossing. So all the pairs AA, BB will count some self-intersections. Not all of them, as Renee very well pointed out. And notice that this doesn't depend of what is the curve word in global. It's just I can have any curve word that I want as long as it contains AA and BB. I will have a crossing. Moreover, every occurrence of the pair AA, BB will label a different crossing because we label a different pairs of segments. Okay, so now let's go to the other. While I did the red, we have a similar thing. So if you look at this red point, I put it in red. It shouldn't be red. I put it in red to highlight it. This, I think it corresponds, let me remember. Go to B and go to A. Yeah. So this corresponds to this point here, the gray. Wrong color. So what happens here? Well, if I look at these two segments, I don't know whether it's a crossing or not. This corresponds to if I have a capital A, means I have A, and this is A, B. If I have AA and AB, I cannot tell whether there's a crossing or not between the segments. How can I do? Well, what you do is you go to the past. This is a psychoanalysis of curves. So this came from here. I think here are the two highlighted pieces. So this piece came from here, and this piece here came from here. So I look at one stage, and now they separate. So here I have a crossing, and this is a picture in a more general way. So the picture says, if you start in different edges, this is the unrolled surface, and you don't need to unroll it really. You can, it's complicated to look at it the same. But you start in different edges. You go to the same edge, and then you may go together, kind of parallel for, 1,000 edges, and then at the end, you do like this, or you do like this. Well, you know which one implies intersection and which one it doesn't. And interestingly enough, this only depends on what happens at the beginning and at the end. There's three letters here, this, and this, labeled these three edges, and three letters here. And the relative positions of these 6 letters will tell me whether this is an intersection or not. And you can have also same thing, but now the segments go in the opposite direction. So I'm going like this. Same idea. So these words have the property that they are one letter, then same word for same word. These two, the blue and the red, had the same word, and then a different letter. So these are the three. These I call the link pairs. And the theorem I mentioned last time is that if you have a deformation class of curves and you pick a representative with the smallest number of crossings in the class, each self-intersection point in your representative can be labeled by one of these pairs of subwords. So it's like there are certain preferred pairs of subwords that will imply an intersection. There's a long list. The list is infinite. There's a long, long, infinite list. And if you find a pair of subwords, an occurrence of a pair of subwords in your word, there's an intersection. Any question?
The linked pairs are explicitly determined given the surface word?
Yes. Yes, because it's this picture here. It's this picture here. You know, these three, the three letters here and three letters at the end, and how they are placed with respect to each other will tell there's a crossing or not.
But there's some sort of algorithm to compute this?
Yeah, there's an algorithm that is there in my computer. Lots of my math life from there. Yes?
These are not octagons. And you were saying this corresponds to twice with one boundary component.
These are just, they're not octagons, but there's some polygons. It doesn't matter. You have to start with a surface word that has a 2n-gon. Okay, you make n cut, you have a surface with boundary. You make n cuts, and then you get a 2n-gon. And then you're going to, find a surface word. But this is another surface. Yeah, these are decagons, yes. No?
So you're saying that it corresponds to the unrolled torus with one boundary component.
Did I say that?
That's the
Okay, I lied. I'm a liar. Can I do? No. This is any surface with boundary. Lolly was in my class. You have to be honest because she catches. It's good. We need her. So this is done and done. Okay. So I called, and you'll see later on why, the set of deformation classes of curve on a surface pi0. And if you know a little topology, it may sound weird, but I have a reason that I'm going to reveal later. So when you have a deformation classes of curve, if you fix a surface word, there's always a choice of a surface word, then you can compute the word length of your deformation class. It's the number of letters in the word that labels that class. That's an integer, non-negative integer. And if you know a little topology, you know that the fundamental group of a surface with boundary is a free group. So choosing a surface word is the same as choosing a set of free generators of that free groups. And now we can assign another number, which is the self-intersection number of the curve. That doesn't depend on the surface word. It just depends on the class of the curve. So these are two numbers. And what we're going to do now is studying relations between these two numbers. No question? OK. So more repetition. So as I said, there's an algorithm to compute the self-intersection number, and well, there's obviously one can compute the length of the word length. Just count the number of letters. So we can make a table. So this table, for instance, in the row 1 and row 2 and column 1 is going to contain how many deformation classes you have with one self-intersection and 2 letters. So the column tells you the self-intersection number, the row tells you the number of letters. And in the corresponding entry, you put how many deformation classes you have. I'm going to talk a lot about this table, so if you have to ask something, go ahead. Is it clear? Here I just saw there's a line that evaporated. It's here, because we can have self-intersection 0. These are the simple curves. It should be there, very important. No question? Okay, so here I have some examples. So for instance, we are looking at the torus with one boundary component, and we have 4 cyclic reduced words with 1 letter and self-intersection 0, which are the 4 letters A, B, capital A, capital B. This one, if you make the picture, you'll see that all these letters, all these words, A, B, capital A, capital B, etc., they have self-intersection 0 and obviously 2 letters. And here we keep going. I mean, those you can compute by hand. Later it becomes much more complicated. So this is a table now up to 8 rows. See any pattern? There's zeros that appear. Anything else? Well, we'll see more. Let me show you. This is a bigger piece of the table. And this is an even bigger piece. Oh, no, sorry. This piece I wanted to show you because yesterday we discussed power and non-power words. In the table, I didn't say it, but I am plotting non-power words. This table contains power words. And as you see, there's something that for me looks a little annoying, that here you see there's a 0 in the middle. The non-power was prettier. They didn't have this kind of not nice pattern. We like patterns. So in some sense, this says that the non-power are more natural to study this because, patterns are, something we can understand and gives you nice theorems. So I'm going to keep now with non-power words. So here is the table, same table for power words.
Moira, I wasn't here yesterday. What is a power word?
Oh, a power word is a word that is a proper power of another word. For instance, AB, AB, AB. There was a discussion, why are you, some people felt like I shouldn't left out the power words, which is true, but depending on which application you're doing, you left it out or not. So this is the table now. I love that picture. I shouldn't say that is my picture, but I really like it. So this is the table, and this picture, what it shows is the following. Here I have the entries. Black means 0. And then light colors means there's something there, but not much, in a small number. And the red you are, the higher the number you have, if you are an entry. So what do you see? Should I point out my accusatory? Yes?
It gets very red, but then it goes back to...
It gets right. So if you look at, even from here, if I look at, this is a row. These are all the words with the same word length. And I'm organizing by self-intersection. So this tells me, well, here I don't have many that are simple or low self-intersection. But if I go more or less to the middle, I have much more curves. And then I go again, and this is the possible maximal self-intersection I can have. I don't have a lot of them. And in each row, this happened. Any other pattern? Like anybody can guess, it's a guess, but what is this shape here? I know it's a wild guess, but it's a quadratic. It's a square root or quadratic, whether you're laying down or... Yes. So let's study the rows of this table. So this is the row 8. I separated. Now I'm going to draw a histogram, and the height of each rectangle will be proportional to the number of classes of curves I have in each entry. So here you see how many simple ones, a little bit with self-intersection 1, and I grow. And now here I have the same histogram, and I'm growing. So here we have word length 4, 6, 8, 10, 12, 14, 16, 18, and 20. What pattern do you see? I want a new voice. Somebody who never said a word. They say Gaussian. Yes. So I was playing with the computer. That was really, I was playing. And then I said, oh, let me look at this row. And then suddenly I saw this. And I was like, boink. And then I wrote to Steve Lally, he's a probabilist in the University of Chicago, and I said, I think the distribution of self-intersection, when you sample by word length, is a Gaussian. And he said he worked in things with another way of sampling, and he said, well, I don't think so. So I just sent him this picture, and he answered, let's prove it. Later on, he said, he works in probability, he does breakfast with Gaussians, and he said, I never saw from an experiment such a, so pronounced Gaussian. Of course, what happens is that, how many cyclic reduced words we have with word length? This is 20 here. Can anybody give me an estimation? How many deformation classes of curves we have of word length 20 in the puncture torus? Yeah?
I did say like 80,000.
Okay. But I want an estimation. No, but remember this is exponential. The number of, every time I add one more length, I can put 4 more letters, kind of, so, or 3 more because the words are reduced. Huh?
More or less 4 to the power 20 divided by 6.
Yeah, it's more or less 3 to the, right. So it's an enormous amount. So of course this is an enormous number. So when you are trying to estimate things, it gets really big, so this is, I'm looking at all the population, this is an enormous population, so I have, a good, if this is goes to a Gaussian when the word length grows and grows, I have a good chance that it will look really like it looks. But on the other hand, I'm going to discuss the theorem that there's a limit when the word length goes to infinity. And this is just 20, 20 is peanuts. Of course, every number is peanut, but 20 is more peanuts than other numbers. So really, it's amazing that you get that with such a low, stage of our sequence.
It's really surprising that it's a Gaussian, seeing that like the situation is really asymmetric because there's like a sharp cutoff.
Okay.
Right?
Well, but very good observation. So here, the mean, the mean of the Gaussian happens when you have in the middle. So here is 20 squared divided by 9. So the mean is not 1 like in a normal curve. The mean is shifting. The longer is the word length, the larger will be the mean. You can get more and more self-intersection when you have more and more letters. So then, what's your question? Oh.
So where's the cutoff? Where does it become 0? Because like
This is the limit of this goes to a Gaussian. That's a limit.
I get it, but for 20, like for
what is the maximum? The maximum is this. You're asking what is the max?
yeah.
The maximum is this, which is about, 80. But it grows and grows and grows. I'll discuss that too. What is the maximum possible? It just goes to infinity, the maximum. Okay, I'm not going to do this because I have little time. So here is the theorem, what we already saw in the picture, which basically says that this distribution, goes to a Gaussian, and we were able to compute, the mean is some constant times, the constant depends on basically the number of cuts you do in the surface. So there's a constant, the mean is a constant times the word length squared, and the standard deviation, let's say the variance is this constant, complicated rational function, times L cubed. And here is something I discovered just browsing probability book, which is, suppose you perform the following experiment. You have a disk, and you're going to throw sticks on your disk. And say the probability of your stick hitting a pair of endpoints on the disk is uniformly distributed. So you can say, well, what is the expected value of intersection number of that experiment? Well, it turns out that is about n squared divided by 6. N is the number of sticks. N is the number of sticks. And notice that when I have a surface that has an enormous number of cuts, surface that is very complicated, lots of genus or lots of boundary components, this goes to 1/6. so that was very pleasant to discover, you know. But then the variance is about NQ divided by 45. And if you look at this, when the number of cuts goes to infinity, this also goes to 1 divided by 45. So it was so pleasant, you know, seeing the 45 showing up in this different, I mean, it's the same thing, because basically what happens is when you have a surface that has an enormous number of cuts, basically, you know, a random curve, the curve that you expect, is just like throwing n sticks on this polygon with an enormous number of sides, which is like a disk. Okay. And then there's analogous results for surfaces with boundary proven by Matt Broughton. Okay, so let me skip because I'm going a little too slow. If somebody's curious, I'll ask me. Okay, here. Now, here is another thing we're going to do with the same table. So now I'm going to have, again, you know, my columns are self-intersection number, rows are word length. But now in each entry, I have this quotient. I'm going to have how many classes I have up to, before it was equal to, now it's up to the row number, and the self-intersection is given by the column. So you know, I have the previous table where it says how many I have on the nose, and then I'm going to, this contains the sum of all of this in the previous table.
So it's like the sigma versus beta.
It's like what?
It's like the sigma versus beta from Moon's lecture yesterday.
Yeah.
Is that what? Sigma?
Sigma versus beta, the sphere versus the ball.
Sigma?
If we can.
Okay. Oh, you. Okay. Yeah. I was thinking, what did I say? Sigma? I didn't use sigma. Okay. Yes, exactly. Sigma versus beta. I should have caught that, you know. So I don't know if you can see the numbers, but what I did is I colored numbers that are close, so we see. So again, I have in this sum, and I divide it by L squared, you know, the row number. So notice what happens. The columns, when they are large enough, they are close. So what does this tell us? Can you make a theorem out of that coloring? No? Yeah, so if the number of, this tells me, for instance, this says that the number of, these are the simple curves, the number of simple curves I have of up to word length L grows like this constant, say 127 times L squared, because this is the ratio here. Notice that all the columns, you know, is L squared. They grow like a constant times L squared. This constant here is given by these numbers. Of course, now here I'm much less lucky than I was when we are counting all the curves, because simple curves are very few. In the previous picture, we saw they were white. You know, this is like you have nothing. I mean, there are very few compared to all the, you know, if you look at all the curves of the same word length, it's very hard to be simple. So here my sample is pretty small when I'm measuring. So I have less hope that I will get a quick convergence. But still, you see something. This, remember 127. And this is, I'm pointing this out that, well, this is late. OK. And this is what I already said. I forgot I made another slide. And just to see another thing is like, this is a plot of the constant. So here is the constant for self-intersection 0, 1, 2, 3, and 4. What's that function? What type of function is that? Jenny?
Is that exponential?
Yes. You see, I threatened you that I will ask questions, and I didn't want to lie in that. Yes, it's exponential. This is a guess, you know, with like everybody, I just trying to make you think. So all of them, because there's the growth of the whole row we know is exponential. If I add up all the rows, they are all the words of all the cyclic words of a certain word length. That exponential growth. Now each column grows, like L squared. Well, how can I put these two facts together? Well, I need that the constant, is varying a lot. The longer is the self-intersection, my constant gets larger and larger very fast, exponentially fast. Oops, okay. And well, this is, as I said, it's all L squared, but here the L squared is, is for the torus with one boundary component. In general, the genus and the number of boundary components will give you the exponent. The more, the more complicated topologically, the more genus or more boundary components, the larger will be the exponent of in this type of thing. Okay. Oh, here, this is. I'm still working on this. We're almost done. But here is another table. Oh no, sorry. Erase that. So here, this is a table for the same table, but for the pair of pants. Same table we did before. We're looking at all the cyclic reduced words labeled in deformation classes, organized by word lengths and self-intersection number. And this is what happens when you look at the table big enough. Now again, the color here, it seems like you have the same number. So there's these funny patterns that you see that this sequence. I have an undergrad student working. He has some we are finding a good explanation of why this happens. Basically, the pair of pants to increase self-intersection, you have to go around the cuffs, and to go from say this one to this one, which had the same number, you have to go in a certain way around the cuffs. When you go around the cuff, you increase the number of letters. So anyway, there's a combinatorial reason why is that. Still, not totally proved, but almost there. And what else do you see? What are the patterns you observe here? This side is very quiet.
What happened with the white if there's no pattern?
There's no pattern that I can see. But any other pattern?
It's almost diagonal. It's slightly off.
Here is almost diagonal. Yeah, that's a theorem. Like first, you have zeros. Remember that, when we look at, say, this column, oops, okay, technology. When you look at this column, I have to be far. Oh. When you look at this column, what is it? Oh, okay. Well, I'm going to use my finger. That is very good and never fails me. When you look at this column, in the torus with a boundary component, we saw that there's always curves there, and the growth is like constant times L squared. Now here you have finally many in each column. So the pair of pants is a very special surface. The ones of you who study mapping class group, the mapping class group is finite, has nothing. And this, it's not hard to see. You can prove it in the review session probably that, there are finally many, well, if you prove that there's finally many simple curves, then this implies that there's finally many for each self-intersection number. This is the only complicated surface. Complicated, I mean more than 2 cuts to get the surface word. 2 cuts or more that has finally many. All the rest, has infinitely many curves of any given self-intersection. And yeah, this pattern, it's a theorem that, this is the smallest. So each word length has the smallest possible number of self-intersection number and the largest one. I mean, it's always the smallest, but the smallest is non-zero. Okay, now I did a little bit like, this is another set of generators. Now, erase what you learned about, cutting surfaces, and remember Moon's lecture. We're going to look at this ABC words, and you have capitals too, but we're going to add one relation. We're going to say that A times B times C is 1, or A times B is equal to C minus 1. So we're going to count the words there, and of course, we're counting as elements of a group with this relation. So this is what we get. We're writing the words, again, in a different alphabet. So again, we see the patterns and these colors. Now, the colors don't color things that are nearby, but colors a very nice pattern. This is joint work with Tony Phillips and Kurt McMullen. And the pattern is that if you look at this red diagonal, you can describe the numbers by a quadratic polynomials. Meaning I have these quadratic polynomials. When I plug in the 0, I get the 3. When I plug in, well, this is 3, but I plug in 3 in the place of n, I get this number. When I plug in 4, I get this number, and so on. So we have these quadratic polynomials that describe all the curves in the pair of pants when I change my alphabet. Any question? Yes?
Is there like a good reason to choose that relation? Or an interesting reason?
Good question. Well, this started because we first studied the standard way. When you have a free group, you choose a minimal set of generators, and then we have what happened. And Tony was saying, well, the pair of pants have 3 boundary components. It's kind of artificial to pick 2 out of the 3. You have to make a choice that is not canonical or natural. So let's put the 3 of them and see what happens. And this happened. And then, of course, we did differences to find polynomials. And there's another, it's funny. So here are the polynomials. And, oh, gosh, did I? Oh, yeah, no, good. Oh, my time is. So now, remember this quadratic or, square root that you found the pattern? Let's see. So first, if you have a certain set of deformation classes in a surface with boundary, and the word length is L. Can you find an upper bound on the number of crossings? Huh? Why? Right, so exactly. L squared, even L times L minus 1 divided by 2, L choose 2, it's the first bound you can have, because these are like lines. So the more time, every pair, the more time they can cross each other in pairs is once. So L choose 2 is an upper bound for all surfaces. So if you have word length length, L squared divided by 2, it's the first upper bound. But there are better bounds depending on the surface. So here we observe this quadratic. Don't lose hope with this. So here we have this quadratic curve, which is there again. And we proved that in fact this is what was the name? Eventually quasi-polynomial. We found this eventually quasi-polynomial. The maximal self-intersection number is given by this eventually quasi-polynomial. So if you have a certain word length, this is your maximal self-intersection you can have if your word length is even, and this is the maximum you can have if your word length is odd. And the proof is, the idea is cutting and pasting curves and trying to make the intersection as bigger as you can. I can talk about it in other lunch if you want. Yes?
Are those realized or are they just upper bound?
Yeah, no, they are realized. Yeah, this is the sharp upper bound. Yes?
And is the eventually part used? Is there a threshold before that starts being true? Immediately true?
I don't remember. I think it's probably eventually needed, but I'm not 100% sure. And this is the table we did with the ABC alphabet. And then let's study differences. So here I record. This one also seems to follow a quadratic thing. Let's see if we have an eventually quasi-polynomial. So we learned that we have to do differences for that. So in the table here, this is the word length. And here I record the maximal possible self-intersection for each word length. And then here I make the differences. But no, the differences, if you could read, I don't know, is, maybe I can show you. Oh no, PowerPoint doesn't let me. So the differences are not one minus the previous. It's the differences are this, sorry, no, here, this minus this. So 1 and 3 up. So 5 minus 0, 7 minus 1, and so on. Because it turns out that we have 3, polynomials in our eventually quasi-polynomials. So these are the first differences. These are the second ones. So this tells us the maximal self-intersection give me this also, this eventually quasi-polynomial as before. And let me skip this. There's also something else. OK, I have a little bit. I'll start with this, and I'll repeat next time. So let's look at curves in the torus. This is the closed torus. Now, no boundary component. How can we describe this curve? Anybody? Well, we can see how many times there's like 2 directions. How many times we go in this direction, and how many times we go in this direction. It's a curve with no crossings. So, you know that the fundamental group, now I'm going to the fundamental group, is this free abelian group in 2 generators. So this says, and if you don't know fundamental group, you can just take my second statement that each deformation class of curves in this closed torus can be labeled by a word. Now the words here are different than the one before. It's a to the something, b to the something. Because here in the closed torus, ab is equal to ba. We can discuss that. So then here we have, in some sense, the deformation classes are much less complicated in the closed torus. So which of these classes are simple? Which of these classes can be drawn without crossings? Any guess? So, for instance, A is simple, B is simple, A times B is simple. ABB, what do you think, is simple? Who thinks ABB is simple? Who thinks it's not? You lose, haha.
I should know better. It's hard to play with.
No. Okay, this is now mommy advice. It's perfectly fine. You thought your idea and you defended it, even amongst, the big crowd. It's great what you did, I mean, I'm not expecting anybody to, if you are doing my research right now and are, know everything, why are you here? I mean, really, sorry to be, doing this preaching, but it's perfectly fine to answer and be wrong. I mean, let's be wrong. And no apologize for it. I mean, not try to be wrong. Try to understand. So now, how can I get a curve with crossings,
We both thought A squared, B squared.
A squared, B squared.
Has a self-intersection.
A squared, B squared has a self-intersection, yes. Now, exactly. It's like, let's look at the simplest curve without crossings, which is one of the simplest. Say A squared or B squared. Here, there's no way I can go twice around without crossing myself. A squared and B squared is AB all squared. So yes, as Murphy said, the classes that are simple are those that these 2 numbers are relatively prime. Because if they are not relatively prime, you write it as, a word to some power, and those words, if the power is larger than 1, they have crossings. So let's do a little, unrolling again. Sarah unrolled the torus yesterday. It's so beautiful. So here we're unrolling the cylinder. So remember that, we unroll. Now what happens, with the curve? So suppose I have a curve, a non-trivial curve, say the curve going around here, what will happen when I unroll it, the cylinder? It gets just like a line, yes. Now what happens when we have a curve in the torus and we unroll it? So here I'm unrolling the torus, but I have 2 directions to unroll. Gosh, I like doing this, It's really, really, because this click is like the click of my mind. When I see these pictures, I really, I need it. It's not like doing it for you. I don't do it for you. I mean, I do it for you too, but I do it mostly for me. So here I have a curve. This is the AB curve, the purple curve on the torus. And here happens when I unroll. So see, I cross in AB, 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 etc. Of course, this curve, maybe I could also draw it going from here to here straight. This is another member of that deformation class. And it's very useful to unroll it to study, their crossings. So this unrolling, we can use the, more technical name is the universal cover. And here I have a curve. The curve is, well, this depends on this is how my edges are labeled. This is different than the surface were, because remember now I'm in a surface that is closed. So here I'm going twice in the direction of A inverse, 3 times in the direction of B. Of course, if I draw this curve in the torus, this go over itself because all this, gets identified. So we should draw it nicely. And this is another member of the class that will have a nicer picture on the torus. So suppose this is going back to moon lecture, how many free homotopy classes, these are cyclic reduced words of word length L I have in the closed torus? L plus 1? L plus 1? How many I have? Why L plus 1?
0, L, 1, L.
Right, so let me see. Right, so if I fix 1, if I fix the exponent of A, I get the exponent of B. Since you have also positive and negative, maybe it's twice that, but it's more or less that. How many simple ones do we have?
Nothing. You just want pairs that are co-prime and add to L.
Yeah. So just something in my brain is clicking and time is going by. Right, so this is the number. The number is how many pairs of numbers that are relatively prime and add up to L. And that's the Euler function of L. And there's a 4 because you have to look at, the different orientations, the 4 quadrants. So my last, have a minute, let's say. So now we're going to look at the torus with one boundary component. So these red dots you see here are holes. They're boundary components, like there's nothing inside the red. So we have this curve. Now this curve that I wrote, the orange curve, cannot be deformed into the one that we had before going this and this. Because when I grab my curve and try to deform it, this boundary component stops me. Okay, I get stuck there. In fact, as we discussed, when we have a boundary component, there's a unique word, and now the order of the letters is crucial. So here I go, in this case, you cross first the capital A, then the B, then capital A. Am I doing it correct? Well, you can do it better. This is not arithmetic, but kind of. So I follow a certain, depending on which edges you cross, you get some word. So how many classes we have here? In the torus. It's about 3 to the L, remember. How many simples? We saw that it was about L squared times a constant. Well, in fact, it turns out that it's the same number we had in the torus with no boundary components. For word length equal to L, you need again relatively prime pairs that add up to L to get a simple curve. And the reason is because when you draw this curve in the torus, in the closed torus, but if you can draw it like this, you can also draw it in the torus with a boundary component. You just have to, tweak a little so you don't cross a boundary. But, you have to go 2 in the direction of A and 3 in the direction of B, and they make a straight line. And that will give you a simple curve. And so then we know, let me just put this here and I'm done, that, since this is a sum that comes from number theory, that says that if I add the Euler function of all numbers up to L, I get 3L squared divided by pi squared. I mean, that grows like, that ratio goes to 1. Notice that, this 1.27 that I mentioned, that was the growth of the simple curves in the punctured torus, is very close to 2 times, 4 times this number, 4 times 3 pi squared. And this is the growth we found in that table. Okay, done. Sorry, 2 minutes over.